Our last speaker for the session is Jamey Jacob, who's the John Hendricks Chair and Professor in the School of Mechanical and Aerospace Engineering and Director of the Unmanned Systems Research Institute at Oklahoma State University. He's the author of over 200 papers in the areas of unmanned systems, aerodynamics, plasma dynamics, and space travel. Please welcome Jamey Jacob.
Thank you very much. So first off, nothing really new about inflatables for space applications. They've been around since the early dawn of space travel, going all the way back to NASA's Echo 1. And we've demonstrated the use of these and deployment of these in outer space with things such as the inflatable antenna experiment. And Bigelow, a private space company based out of Nevada, launched two of these, Genesis 1 and Genesis 2, to demonstrate the applicability of this, and has recently even had a module aboard the ISS. And NASA's Gateway space station, which will be in cislunar space, about the lunar orbit, also has a proposed inflatable airlock module. Now, that said, even though that we have a pretty good history with inflatables for space applications, there tends to be a little bit of pushback when you propose this, particularly to the older guard in NASA, even though we have a long history of this, and every space habitat that we use for EVA going all the way back to the 1960s, aka our spacesuits, are also made out of inflatables and fabrics. However, when you start looking at the benefits of some of the inflatable applications, primarily that you can get more volume in a much smaller space and deploy it when you're on orbit, resulting in fewer launches, that attractiveness then comes back and says, well, maybe this is something that we can go back and look at. Now, our history in this primarily goes back to around the late 90s when we started doing this with NASA for development of inflatable wings for interplanetary craft, primarily flying on Mars. In this case, that's a really hard problem because you have a very high aspect ratio or high wingspan that you would like to have due to the low Martian density that you have to pack into a really, really small space. You want to make this really thin, just like a bird's wing, due to the low Reynolds number that you have. And so you end up with these really complex shapes that have to carry a lot of weight and loading. Good thing about this is if you can do these types of shapes, you can pretty much do any other type of shape as well. And we demonstrated this through a number of different flight tests. The one shown here is actually NASA's I-2000 that flew at Armstrong. These demonstrated over here are some of our tests, and you can see one of the higher altitude tests that we flew in a balloon up to 100,000 feet that included some thin film photovoltaics as well to demonstrate that you could also integrate solar cells with this. Now, we've recently applied this to other applications, primarily high altitude kites, looking at things that are really, really low weight, but using inflatables for all of these structural materials, so that way you don't have any rigid elements on board, so that way you can keep these things very lightweight, and using very, very thin films, typically, again, only a couple of microns thick, to be able to keep these things really lightweight. The inflatables here tend to be quite a bit heavier than that, but they're still lightweight. So for a kite like this, you can keep this entire mass under 2 kilograms, and that's about 5 meters or so in span, to give you a sense of the size of that. Now, we've also applied this to analogs for inflatable habitats. Primarily, all of this has been done as part of undergraduate experiences, so most of these are senior design projects that we've been utilizing this with. So this gives the students a really kind of engaging application where they can start to push the envelope and do new things. And so most of this has been through NASA's Exploration Habitat program, which was primarily developed as a way to look at new solutions to problems that NASA has had for a long period of time, which gives them kind of two benefits. One, it's pretty cheap since they're using undergraduate student labor to do this. But it also, they're looking at ideas that typically are outside the box because the students don't know what they don't know. And sometimes they'll propose things that certainly don't work, but then sometimes they'll come up with novel ideas that, will kind of break the mold and do something pretty new and kind of groundbreaking This is an example. This was our first experiment with this. And so this is a inflatable loft on top of NASA's Habitat Demonstration Unit that's down at JSC. And this was primarily proposed as a way to give either the lunar or the Martian crew more living space. And so they threw this out there and said, hey, exploration habitat teams, come up with a solution for this. Now, when we were demonstrating this as part of our public outreach, that's when, someone asked, well, so what you're building is actually a bounce house. And so we had to come up with an answer to that and say, yeah, it's a bounce house, but it's a really highly reliable bounce house for space-based applications. And so that's where the title comes from. So this is an example, that inflatable airlock, which was a test analog for the Gateway mission. Now, there are a lot of advantages to using inflatables. Now, first off, I always try to be agnostic in the use of this. We look at the best solution for any particular application. So inflatables aren't always going to be the best solution. And for the most of the times, they're not going to be the best solution. But there are times when you want to have a lot of volume that is initially going to be stowed in a very small space as part of your launch system, that it does provide a viable solution. Now, that provides you, primarily with this first bullet, that's really mass limited and not volume limited. So you don't necessarily have to worry about the volume of the fairing on your launch vehicle. You really more have to worry about the throw weight that you have that you're going to be able to launch with your system. It is easily stowed, so that way you can use this, to pack in a pretty tight volume, deploy it in some applications. You can even restow it and then redeploy it multiple times if you integrate this with some kind of mechanical stow mechanism. And you can make these into pretty much nearly any shape you want to. So here's an example of an inflatable arch, again, just made out of a single piece of fabric. So you can tailor this so that way your tension pulls in certain directions as you're inflating the system, and so that it can form pretty much any shape that you want it to form. And you have a wide array of material options, from very thin film fabrics such as Kapton and Mylar, all the way up to really heavier woven fabrics, which is what we'll primarily focus on because we have the needs for those stronger materials that we'll display in our notional spacecraft designs. Now, there are some disadvantages to this. First off, you do need to maintain internal pressure to be able to maintain the shape, so you have to have that as part of your maintenance in your reliability matrix. And how NASA tends to look at this is, since we have not been using these for human space exploration for the last 60-odd years, there's a lot less that we don't know about them. And due to that, they typically impose a much larger safety factor when you're using inflatables as part of your design. Where you might be able to get away with a safety factor of 50% on some designs, NASA usually imposes a safety factor of around 4, which really does put a strain on your weight. So you do have a weight penalty due to those safety factors. Good thing is, as we're learning more about these and we become more confident in their performance, that imposition is coming down, albeit gradually. Now, there have been a number of inflatable habitat concepts over the years, primarily looking at lander applications, both for lunar and Martian surface, as well as orbital applications. In addition to the Bigelow Beam experiment, which is currently on board the ISS, which was recently extended in terms of its mission duration. So they've had really good results of that. They're looking at other applications as well, with possible demonstrations of centrifuges. And so you have lots of options here that you can actually pull out of the literature that you can use as part of a baseline. And for those going to the cosmosphere, you will see the Russian or Soviet Volga airlock, which was launched back in the 60s and demonstrated the first EVA capability. So there is another one in a museum in Russia. So the fact that there are only 2 of these existence in the world, and one of them is here in Kansas, is certainly a good reason to go off to the cosmosphere, in addition to all the great other artifacts that they have. Now, talk a little bit about the engineering of these, and it's actually relatively simple, so it's not very complicated from a physics or engineering standpoint. Primarily what we're looking at is the stresses in the skin. Since these are inflatables, we only have to worry about tension. The skin does not hold any compressive loads. So we really have a simple relationship between the stress in the skin given by sigma here and the internal pressure. So we only have to worry about, the size of the habitat that we're dealing with, or whatever inflatable structure that we have, as well as the internal pressure. And for the most part, since we're looking at using these for habitat designs, we're primarily going to be basing our internal pressure around atmospheric pressure. Of course, if we increase the oxygen percentage, we can lower that pressure a bit, but we're going to use pretty much 1 atmosphere as our baseline for all of our designs. So then your only variable primarily becomes your size of the habitat. Now, if you go from a sphere, that's your simplest formulation that you have, going to a cylinder, and then finally a torus, your relationships become slightly more complicated, where you're looking at the axial and the hoop stresses for the cylinder, and then you have a circumferential loading as well on the torus. However, all this is pretty easily derived and has been pretty well known for the past 60 years. So we're very familiar with these relationships. The other piece of this is the bending, and so particularly if we're looking at things such as cylinders that we're putting on board habitats that may be accelerating with a load on the end, there is going to be exposure to bending loads. So for example, if we have an inflatable boom here, and whether this is rotating or whether this is axial accelerating, if we have a load on the end here, you will experience bending at the root of this beam. So we can go back to the well-known Euler-Bernoulli beam equation for that, and then just adapt that based upon the moment and our cross-sectional moment of inertia for a fabric beam to a slightly more complicated equation. Now, since we don't have the ability to withstand compressive loads, how this fails is when you get to a point where your tension at the bottom or your compression load at the bottom reaches your sustainable stress that you have in your skin, you start to get wrinkling, and then your beam fails. So we'll see that here, and this will just demonstrate that when you have this formulation, you can actually solve by setting your skin stress equal to 0 based upon your internal load, which determines your tension, and then your bending moment that you have. Now, just like any other beam, you have the very familiar load deflection curve. You get up to a point where instead of having that yield stress, what you'll have is you'll have a wrinkling onset at the bottom of the beam, and then at some point after that, you'll start to have actual bending. So a good thing about this is, first off, when this fails, it's not disastrous, because as soon as you remove the load, it snaps back into place. So even though that you consider this a failure under your loading conditions, you have not destroyed your beam in this case. The other good thing about this, you can actually use this for control. Based upon your internal inflation pressure and your local diameter that you have, you can control at which point your beam is actually going to bend. And we'll see some applications of this later where you can use this for in-flight control. And so you can tailor your beams to be able to essentially act like relatively primitive air muscles, where you can change that amount of inflation pressure, and all we're doing here is changing the amount of inflation pressure that's going into this beam under a certain imposed load. And in this case, that's just a simple beam. You can also add tension elements in there, things such as simple as bistable composites or tensioning elements either on the top or the bottom to help control that in other creative fashions. Now the next piece of this then is the material. So based upon your design loads that you get, or that value of sigma, then you can go back and determine what your material properties are going to be. Now, since these are for space-based applications, we want to try to make these as light as possible. And we have a number of materials that we can actually choose from. One of the common materials that we use quite often is just a polyethylene-coated nylon. very similar to what you would use for camping materials or dry bags or the like. Very lightweight, impermeable, so that way it holds in the gas and you don't need to have a separate bladder. For some of the higher load applications, we use things such as Aramid, aka Vectran, which were used on the Martian airbags. And so you'll have a woven fabric like this, which is permeable. In that case, you'll need to use a lightweight bladder on the inside to be able to hold in your gas. It does also alter your equations a little bit since you have a woven element in there, but again, that's relatively straightforward. Now, the other piece is if you're making relatively large structures, you also have to be able to join these. And that tends to become your weak element as you're going up to larger and larger loads. So that way you need to be able to be cognizant of how you're actually attaching these materials. Whether you're using something like heat seals or sewing them together, or actually using other external straps to be able to make sure that you're not overloading that particular beam that you have. Now, we'll go ahead and jump into a implementation example. So there are a number of options that we've been looking at for possible interstellar travel. And the primary driver behind this is, since we're going to be on a very long duration mission, we want to be able to generate artificial gravity, and that's been the primary driver for the implementation example that you've seen, although we've been looking at a number of different examples as well. So if we're looking at this from the aspect of being able to generate artificial gravity, again, there's a lot of unknowns about where we want to be at in terms of the how much G load you actually want to generate, the size that you're driving from. So we've gone back to Hall's paper and used his derivation of this comfort zone as our set of driving parameters. Again, this target zone that we have here is essentially a balance between having enough of a G load so that you're able to maintain your muscle mass during the mission, as well as having a large enough radius so that way the gravity gradient between your feet and your head doesn't induce any dizziness or nausea. So this leads to a relatively large radius. You'll notice here that we're getting into the 20s to 50s to hundreds of meters in terms of your radius of your system, as well as to a relatively modest rotation rate, which is going to generate an additional load that you're going to have on your inflatable structure. And so you can argue about whether this is too much, but again, that's used as our baseline. But that's relatively easy to go back into your matrix and change those values, so that way you can reduce or increase if you need to. Maybe you want to settle some planet that has a gravitational acceleration of 5 Gs, so you slowly ramp up your crew as you're working towards that destination. So this is our point of departure design, and the piece to focus on here. All the rest of this is just really kind of science fiction fluff more than anything else. It's really this front piece right here, where you have your habitats on either side. In this case, we have included, beam-like or Bigelow-like inflatable habitats is the inflatable connection module that you have here. So that way it makes this relatively easy to launch this either on single or, maybe a set of SLS launches, attach them together, and then you can deploy this either on orbit or when you're on your mission, and then start the overall rotation process. So the overall size and diameter of this is determined by the inflation pressure, access ways, so you can actually use this to be able to go back and forth between two modules. Again, this is based upon NASA's tethered concept, but in this case now you can use this entire internal volume not only for living space, but also to get back and forth between the two modules. Now, I won't go through the details here. I know there's a lot in here, but you can just go through the paper to pull out these individual components of this. But the things you should actually focus on here is we are still using that factor of safety of 4 that NASA dictates for most inflatable applications, and we're still an order of magnitude under the imposed stresses that we have within the skin. So we have plenty of safety margin to work with, and quite a bit of mass on both sizes There are a rotating Torus here that we have, plenty of both volume and space for our crew on board this. And this is just a single component. You can add as many of these as you want to in order to increase your crew allotment or amount of materials that you're taking with you. Now, to demonstrate this, a couple years ago we flew this on board NASA's Weightless Wonder, aka Vomit Comet, to actually demonstrate the deployment capabilities and primarily some of the unknown physics as you're taking this and deploying it outward, looking at the various deployment mechanisms, how you're actually folding the fabric up, how fast you're deploying this. Are you deploying it and then rotating it, or are you rotating it and deploying it at the same time? Now, keep in mind this is a scale model, but we dynamically scaled this, as best we could to be able to, demonstrate that we could still get 1G loading on this. And so here's a video. Now, I don't have a lot of great video of this because we did have cameras here that were taking video that we used for the data analysis. Most of the video that I got back from NASA, usually has a student crew doing somersaults or lunar push-ups or stuff like that, and not enough about the science, or high fives and saying hi mom and all that kind of stuff. But you can see the video here in terms of deployment. Now, for those of you not familiar with this, you usually only have about 20 to 25 seconds of useless time in your microgravity environment, which, depending upon the quality of your pilot, varies somewhere, say, between minus 0.05 to plus 0.05 Gs. Then you have to go back and reset your experiment and start over. And we did about 40 of those parabolas to be able to get enough data and vary the setup parameters for that. Now, just a couple of these is primarily just demonstrating what happens during an actual deployment sequence. So this is the rotation that you're feeling on either side of these. So we're using small accelerometers, wireless accelerometers mounted on each of our masses to demonstrate the capability of your habitats, or serve as analogs for your habitats. That as you're going through the deployment phase and then the actual rotation phase, that you get something similar to what you would expect in a artificial gravity type of environment. And keeping in mind that this is a relatively small rig, which is susceptible to small vibrations and intricacies with the stepper motor and the microgravity environment that you have, you can maintain a reasonable value of your required 1G acceleration in either side of your habitat to sustain that artificial gravity environment over a long duration of time, and that you're not getting any oscillation once you've inflated to your full inflation pressure. So the flight test results here, you can actually see deployment when it's still under inflation, and this was one of the tests. We were rotating and then inflating, so that way your masses pull out the uninflated beams to both sides. And you can see here where it shows an example of that buckling environment that you get at the root. As you're rotating around and you have the load on the end, it overcomes that compressive failure that you have at the root of the beam, and then basically collapses. But once you're fully inflated, you get something that looks a lot like that. Now, you can then alter this. You have a lot of design variants. You can go to something like a toroidal structure or a von Braun wheel, where you have multiple inflatable beams along with an inflated torus. And so, you have nearly an infinite array of different types of design options that you can choose from. Now, just to kind of summarize, I'll go through these pretty quickly here. So we have looked at a number of arrays, such as coming up with more complicated designs, such as a RAMS group, as well as different inflatable habitat designs, and asteroid capture systems, which you can do by changing pressurization in different beams as part of your structure, having one set of beams inflate when you're ready to capture, and then another set of beams inflate when you deflate the others to be able to essentially do that grab maneuver. So, using your inflatable beams essentially like air muscles in this case. So I think with that, I'll go ahead and conclude. So if you want to just throw up my summary slides there. I'd be happy to take any questions if there are any.
I imagine that the inflatable materials have some type of self-sealing properties with collisions, but what are the limits of those, both in, say, cross-section and momentum of dust particles colliding outside?
It is going to be an issue, and you can go back to a couple of examples, something like this, where you have a really thin film. That's going to be no different than you'd have, say, with a solar sail. As you move up to the more complex, fabrics, where you actually have a woven structure, those will have a greater ability to resist particles, particularly dust particles that you're able to collide with. But it's not necessarily going to be self-sealing in that regard. So it really just depends upon that outer restraint layer. And we kind of treat these just like you would with any other type of habitat structure or a spacesuit where you have multiple layers. You're going to have, your protective layer and your restraint. That's going to restrain all of your hoop stresses and axial stresses that you have. But you'll also have protective layers for, radiation protection, dust protection, and then thermal protection. So you'll end up with multiple layers, throughout the entire inflatable structure. So it really just depends upon your expected environment that you're going to be in and what those layers are going to look like.